This is Calculus 2 video lecture number 1 on integration by parts. And we're going to kick off this video lecture series by looking at different integration techniques, the first one being integration by parts. So the formula for integration by parts actually comes from looking at the product rule for differentiation. So if you'll recall, when you're taking the derivative with respect to x of a product of two functions, f of x times g of x, the result is f prime of x times g of x as is plus g prime of x times f of x. Basically, I think of it like the two functions take turns having their derivative taken, right? Okay, so what I want to do now is rearrange some of the terms in this product rule. I'm actually going to subtract over f prime of x, g of x to the other side. So I have the derivative with respect to x of the product of f of x and g of x minus f prime of x times g of x, and this equals f of x times g prime of x. Good. Now let's just mirror the equation. So I'm going to have, I'll switch which side everything's on, f of x, g prime of x is equal to the derivative with respect to x of f of x times g of x minus f prime of x, g of x. Okay, same equation, just reversed. And now what I want to do is actually anti-differentiate both sides with respect to x. That's why I left some space there. So integral sign dx, right? I'm anti-differentiating with respect to x, whole thing, both sides. Here we go. Nice. Now, the left-hand side, I'm going to leave it as is. So I have integral f of x, g prime of x dx. And then notice here on the right-hand side, so if I'm integrating with respect to x, the derivative of f of x times g of x, those are just going to undo each other. So I get regular old f of x times g of x minus, and then I'm just going to distribute that integral. So I have integral of, and I'm just going to switch the product here, g of x times f prime of x dx. And actually, this is the formula for integration by parts. Now, typically you'll see it written a little differently. So if we let u equal f of x and v equal g of x, then we have the following. So the left-hand side becomes integral or antiderivative of u. G prime of x dx would be dv. And then this equals f of x times g of x, so that's u times v minus integral. G of x is v, and then f prime of x dx would be du. And more commonly, you'll see it written this way. Okay, so here's how the process works. You have some integral, okay, which involves a product. You need to decide in that integrand what u is going to be and what dv is. So you pick u and dv. So you start on the left-hand side. Okay, so you pick u, you pick dv. From there, you need to find du and v. And I recommend stacking them this way. Okay, and then it's really easy to remember the formula if you set it up this way, because look, so you have integral u dv equals, well, u times v, that's this diagonal product here, right? So u times v goes here, minus, and then you have integral v times du. So you actually end up integrating this product here of that second row. That's what you actually integrate. So notice you don't integrate what I circled in purple. You don't integrate u times v. You integrate v times du. So what does that mean? You want that to be as easy as possible to integrate, this product here. I want this to be as easy or friendly, you know, to integrate as possible. And that'll help you when you're trying to choose u and dv. Okay, so I'll talk you through the process. That'll probably be the hardest part, and don't worry, it's totally normal to set them up wrong the first couple times and then you'll have to erase your work, okay? It's not the end of the world. So here we go. Example time. Example 1, evaluate the following integral. So we have x times cosine of 5x dx. All right, now think back. The only other integration technique you're probably familiar with at this point is u substitution, but no u substitution will save you or help you evaluate this antiderivative, because look, what would you let u equal? It's going to get you nowhere. Try it. Anyways, so let's decide what u is going to be and what dv is going to be. Okay, so I'm going to let u equal, in this case, x, and then dv is going to be cosine of 5x dx. Now, why did I pick it that way? Well, because notice du then is just going to be dx. And then let's see here, v is going to be the antiderivative of cosine of 5x dx. Now, maybe you need to do this aside, and then hopefully you can just do it in your head after I show you this little trick here. So I have integral of cosine 5x dx. So maybe you need to do a little substitution. I'm not going to use u because we're already using it for by parts. So I'll say let's let t equal 5x, then dt is equal to 5 dx. So 1/5 dt is dx. All right, so now my integral becomes 1/5. I have antiderivative of cosine of t dt, and then that's just 1/5 sine t plus c. And then remember, go back and replace t with the original variable. So that's going to be 5x plus c. But notice you don't need to do this substitution, hopefully ever again, for the rest of your calculus career. Because whatever the coefficient was in front of x, right, in this case it was a 5, you just ended up dividing by that. And that's going to be the case every single time, because when you make that substitution or change of variables, you end up dividing by that constant. So if you have some constant times x, when you anti-differentiate, just divide by the constant instead of wasting time doing this whole substitution. Got it? Good. So now v is 1/5 sine 5x. Now, why did I choose it this way? Remember, as I mentioned earlier, you want this product of du and v to be as easy to anti-differentiate as possible. And so if I let u equal x, then du is just dx, which is really nice. And then I can easily anti-differentiate this product here. Okay? So here we go. Back to the original problem at hand. I want to anti-differentiate x times cosine 5x dx, and that's going to equal, so first you have that diagonal product, uv, this way. So that's x times 1/5 sine 5x. I'm going to put the constant out front, okay? 1/5 x sine 5x minus, now you integrate the green circled product, which is going to be 1/5 sine 5x dx. Okay, so this is that first product, the diagonal one, and then you integrate the bottom row's product. Okay, almost there. So 1/5 x sine 5x, that's done. Now I have to anti-differentiate 1/5 sine of 5x. Okay, we don't need to do another substitution. Remember what we just talked about? If there's a constant in front of x, you just end up dividing by it when you anti-differentiate. So I'm going to have another 1/5. So that means I'm going to have 1/25 as my coefficient. And then antiderivative of sine of 5x, it's going to be a negative cosine, right? And so I notice I already have a negative here. So that last term is going to be a positive 1/25 cosine 5x plus c. Don't forget the plus c. And that's it. Okay, now just if you need a little bit of guidelines or help choosing U, just experience practice is the number one factor that'll help you, but you could also remember LIPIT. There's all sorts of different acronyms, okay? This is just one. You might hear other things out there. So logarithmic functions are a good choice for you. Inverse functions, if you see like cosine inverse, sine inverse, then polynomial functions, exponential functions, or trig functions. Okay. Good. Let's look at more examples now. So example 2, evaluate the integral. This time it's a definite integral. We have limits of integration, so we'll look at how to deal with that. Okay, so I have definite integral from 1 to 2 natural log of x over x squared dx. So I'm going to apply the acronym and let's see if choosing the logarithmic function works for you. Okay, so u is going to be ln of x, and then that means dv is what's ever left over. Everyone has to be accounted for from the original integrand, u dv. You can't have part of it be u, part of it dv, and then something's not being expressed or included there, okay? Good, so let's see, what's du gonna be? Ooh, I like it, because derivative of ln of x is 1 over x dx, so that means I don't even have to anti-differentiate natural log anymore. And then what's v? So it's going to be antiderivative of 1 over x squared. Remember, that's x to the negative second dx. So I'm going to increase the exponent by 1 and then divide by the new exponent. So I'm going to have negative 1 over x. All right, so here we go. We're going to take u times v, so this diagonal. I'm going to write it as negative ln of x divided by x. And remember this, I don't need to anti-differentiate, right? Just u times v. But I do have to evaluate it from 1 to 2 on our limits of integration. And then I have minus the integral of the product of du and v, or v du. So that's going to be negative 1 over x times 1 over x is 1 over x squared dx, and the limits are from 1 to 2. All right, nice. Now let's go ahead. I like to finish anti-differentiating completely before I evaluate anything at the limits of integration, so you could just do it nice and clean in one step. Okay, so I'm just going to leave this alone for now. Negative ln of x over x, evaluated from 1 to 2. And then this is going to become plus integral from 1 to 2. I'm going to rewrite this as x to the negative second dx. Okay, and then we actually just did this antiderivative, so it shouldn't be too bad. So now I have negative ln of x over x. And then antiderivative of x to the negative second is going to be negative 1 over x. And now everything's anti-differentiated. So I'm going to evaluate all of it at the limits of integration, which were from 1 to 2. Do you see how slick that is? Then everything's on the same level. It's taking place at the same point. Good. So here we go. Plugging in the upper limit, I have negative ln of 2 over 2 minus a half minus, that's negative ln of 1 over 1 minus 1 over 1. Okay, so this is negative natural log of 2 over 2 minus a half. And then natural log of 1, that's 0, so this guy's gone. And then this negative distributes here, so that means I have plus 1. So I just have 1 minus a half to combine. So that's 1/2 minus natural log of 2 over 2. I mean, they already have a common denominator, so let's just write 1 minus natural log of 2 all over 2, right? Why not? Looks beautiful. And there's our answer. Very good. Okay, let's do another one. This one's a snazzy little fun one. We have this integral here of e to the negative theta times cosine of 2 theta d theta. Now this kind of integral, sometimes they're called ones that boomerang when you evaluate them using by parts. And that's because the derivatives of exponential functions and trigonometric functions like cosine and sine are cyclical, right? We know if we take the derivative of e to the theta or even e to the negative theta after several iterations, I'm just going to get back to the original function. And same thing with cosine of theta. So for this reason, you're going to notice the original integral pop back up, and you'll see what I mean in just a second. So it actually doesn't matter which one's u, which one's dv, as long as you're consistent, because you're going to have to apply by parts more than once, okay? So I'll just let u equal e to the negative theta, but you could just as easily set it up the other way, and dv is going to be cosine 2 theta d theta. Okay, so now let's find du. du is going to be negative e to the negative theta d theta. And then v, okay, come on, we're ready for this. You don't need to actually do a substitution, right? You're just going to divide by 2 since we have that coefficient on theta, and then just think to yourself, what is the antiderivative of cosine something? It's sine something, so just keep the argument the same. So you're going to have 1/2 sine 2 theta. Good? See, it saves you time. Those are seconds of your life you'll never get back. All right, so now I'm going to actually rewrite the original integral. We have integral e to the negative theta cosine 2 theta d theta equals, all right, let's see here. So we have this product uv. I'm going to write that as 1/2 e to the negative theta sine 2 theta. And then I have minus this integral, but I notice there's already a negative, okay? So I'm going to write plus, and then let's pull that 1/2 outside so it's a little nicer. E to the negative theta sine 2 theta d theta, okay? Now look at this integral that we have here. It doesn't look too different from what we started with. So I'm not really in a better position to just be able to anti-differentiate it directly, right? It didn't simplify it in a way where, oh, now I can go ahead and figure out the antiderivative. What we actually need to do is apply integration by parts one more time. So I'm going to call the original integral I. Okay, remember that's what we're trying to solve for or find. That's what we're evaluating. And I'm going to apply one more round of integration by parts just to this integral right here on the right-hand side. Okay, I'm not going to use u and dv because this is our second round. I don't want to confuse it with the original u and dv, so I'm going to have a u bar and a dv bar. Okay, now here's where you need to be careful. Look back at what you let u equal the first round. So u was the exponential function. In the second round, you need to be consistent. So u needs to be the exponential function again, e to the negative theta. Okay, otherwise you're just going to undo what you did. And then dv bar is going to be the trigonometric function. So that's going to be sine 2 theta d theta. Good. So that means du bar is going to be negative e to the negative theta d theta. And v bar is going to be, now this time if I anti-differentiate sine 2 theta, I pick up a negative, right? Negative 1/2 cosine 2 theta. Okay, so let's rewrite what we have so far. You have to be meticulous with these and really patient and detail oriented so you don't make a careless mistake. So I equals 1/2 e to the negative theta sine 2 theta plus 1/2, and then now the by parts action happens. So u times v, that's going to be negative 1/2 e to the negative theta cosine 2 theta. And then let's see, v du, these two negatives are going to cancel. So I still have minus the integral, let's take the 1/2 out actually, integral of e to the negative theta cosine 2 theta d theta. Whew, we made it. Okay, and this is why now these are called integrals that boomerang. Okay, you might say, hey, wait a minute. I recognize this. That's my original integral I. Okay, so I'm going to first distribute that 1/2. We'll take it one step at a time. So I have 1/2 e to the negative theta sine 2 theta minus 1/4 e to the negative theta cosine 2 theta minus 1/4 integral e to the negative theta cosine 2 theta d theta. And if you already recognized at this step that this was I, you could have just written minus 1/4 I. So this is where the boomerang happens. The original integral comes back, pops back out, and you're going to solve for it the way you would just solve for any variable algebraically. Meaning I'm going to isolate it, so I'm going to put all of the i's on the same side of the equation. So I have I already there, plus a 1/4 I equals 1/2 e to the negative theta sine 2 theta minus 1/4 e to the negative theta cosine 2 theta. So now that means I have 5/4 I equals 1/2 e to the negative theta sine 2 theta minus 1/4 e to the negative theta cosine 2 theta. How do I isolate a variable? When there's a coefficient, you multiply by the reciprocal. So I is equal to 4/5 times 1/2 e to the negative theta sine 2 theta minus 1/4 e to the negative theta cosine 2 theta. All right, we're in the home stretch. So now just put it all together. Rewrite what I originally was, okay? So I was integral e to the negative theta cosine 2 theta d theta, and that equals, now distribute this 4/5. So we have, that'll be 2/5 e to the negative theta sine 2 theta minus 1/5 e to the negative theta cosine 2 theta. And then this is the part where you just have to have your wits about you and remember to put a plus c. Yeah? Okay, that can be a little tricky for students sometimes, but you can handle it. Good. So when to look out for a boomerang? Typically, yeah, when you have a product of two functions in your integral and both of them have derivatives that are cyclical. Okay? Trig and exponential is like the most classic combo. All right, one last example. Use substitution first and then integrate. So we're going to use a U substitution first. In this case, I'm actually going to pick a different letter because if we're going to apply by parts after, I don't want to use up U. Okay, so typically we go with T. All right, any choices? So we have definite integral from rad pi over 2 to rad pi of theta cubed cosine theta squared d theta. So let's say you were gonna let t be cosine theta squared. Like, oh, that sounds good to me. So then dt gets you in trouble. Derivative of cosine something is negative sine something, and then by the chain rule you have to multiply by 2 theta d theta. Now things are spiraling out of control, right? Because I have a theta cubed here. I don't even have a sine of theta squared anywhere in my integral. So this is a bad choice, okay? Sometimes you can just imagine the bad choice. You don't have to write it out. If it happens and it's not working out, leave your work. That way you know not to repeat it, or you can look back and learn from it, okay? Don't erase everything that goes wrong. Here's our better choice. Are you ready for it? We're going to let t equal theta squared. Why is that so good? Well, look at my integral. I'm going to rewrite it for you right now. Perhaps it will be enlightening. So we have rad pi over 2 to rad pi. And theta cubed, right? Here's theta cubed sitting so harmlessly. Theta cubed is theta squared times theta. And then I have cosine theta squared d theta. So if t is theta squared, that means dt is going to be 2 theta d theta. So 1/2 dt is theta d theta. And that's actually perfect. That's perfect because 1/2 dt is theta d theta. And then t is theta squared. So I'm going to replace both those theta squareds with t. Everyone's accounted for, okay? And then what's going to be super nice is now these radicals are gone, right? Because t is theta squared. So let's rewrite our integral now, all in terms of t. Do it in one step. No mixing variables. You can't have part of it in terms of t, part of it in terms of theta. That's not well defined. So we have integral from pi over 2 to pi. And then remember, theta squared, that's t. And then I have a 1/2 cosine t dt. Okay, so nice. Let's take the 1/2 outside. Okay, you guys get in the habit. When there's a constant, pull it outside so it doesn't get in the way. So we've got 1/2 integral pi over 2 to pi t times cosine of t dt. All right, it's by parts time. So here we go. I'm going to set it up. I have a u and I have a dv. Okay. Remember, you want this bottom row du and v to be as easy as possible to integrate. If you have a trig function and then a polynomial, right, you always want to let u be the polynomial because when you find du, the degree is going to keep going down and become easier and easier for you to integrate. You don't ever deal with integrating u. So put what you don't want there. It wouldn't be a good idea to let u be the trig function because du would still have a trig function in it, right? It's not going to get any easier. So that wouldn't be a good choice. Try it and see if you don't understand what I mean. And then dv is cosine of t dt. And then v is going to be sine t. Okay, cool. So here we go. Remember, we've got that 1/2 sitting out there. All right, applied to the whole thing. So I'm going to put some brackets now. And then we have uv, so t sine t. And then remember, that's evaluated from pi over 2 to pi minus integral of v du. So that's going to be sine t dt from pi over 2 to pi. Okay. Can we evaluate this antiderivative? I certainly hope so. If not, ooh. Okay, so we've got a 1/2 t sine t. There's already a negative sitting here. So antiderivative of sine t is negative cosine t, but now this is going to be plus cosine t. Everything's anti-differentiated, so I can evaluate all of it from pi over 2 to pi. Don't forget the 1/2. So we've got 1/2. Take your time here. Pi times sine of pi plus cosine of pi minus pi over 2 sine of pi over 2 plus cosine pi over 2. Yes, looks great. Okay, sine of pi, that's 0. So that guy's gone. Cosine of pi, that's -1. Pi times, so sine of pi over 2, that's 1. Okay, times pi over 2. And then cosine of pi over 2, that's also 0. So what are we left with? Oh my goodness, I've got 1/2 times 0 minus 1. And then this negative distributes, so minus pi over 2. And then I'll distribute that 1/2 for my final answer. So I have -1/2 minus pi over 4. So good. All right, so that concludes the lesson on integration by parts. Be sure to give this video a thumbs up, subscribe if you haven't already, and stay tuned. There's lots more Calc 2 videos coming your way.